the Rubik Cube, the ball pen, the match, vitamin C, and things like that. So Hungarians are smart, and we love hacking as well. So both of us are working as security consultants. So we do the usual stuff like penetration testing, vulnerability assessment, configuration reviews, and things like that. And as you can see on the picture, Laszlo has more experience than me and more blood on his T-shirt. Anyway, he's my boss, so that's my blood on his T-shirt, so it's a sad story or whatever.
No, it's fun.
No, it's not. Okay, so just like last year, we have 4 different topics for you. First, we will take a look at the Android phone encryption. We compare it with the Samsung way because they try to think differently. Then we move to the SD card encryption. And of course, we have a lot of tools, what we're going to show you today. And yes, again, we played a bit with Oracle because we love Oracle, and it's always fun to mess around with Oracle. But first things first, let's start with the phone encryption.
But before we, can you hear me? Okay. Before we start, here is a warning for you. We conducted our research on the following device models: S2, S3, and S4. And when we're speaking about versions, we speak about these specific device models. And we mean not only the specific devices, but their ROM variants too. Of course, we did not test all of the possible combinations, such as all US and European firmware versions. What's the point? Android supports disk encryption or phone encryption from version 3, which was the tablet-only build. In case of phones, the encryption is supported from version 4. It's open source, the algorithm is public, well-known, thoroughly analyzed over and over again. It's boring stuff. But Samsung thinks differently. To see the difference, we first need to understand how the normal Android way of encryption works. From the user-supplied password, a key is generated with the password-based key derivation function tool. I practice this a lot. The encryption key is stored, the encrypted disk key is stored in a file or in the partition footer. The encryption key is AES decrypted with the key derived from the password. In order to perform the actual encryption, Android uses the encrypt, which is transparent disk encryption in the Linux kernel. That's why it's quite easy to mount an Android encrypted disk image under Linux. We will demonstrate this later in case of Samsung. The key derivation function uses 2000 cycles. In theory, in practice is 4000. And the de-encrypt using AES CBC. Fortunately, this diagram is easy to remember because it looks like a Desert Eagle.
Guys, do not give a gun to me. Never, ever.
Anyway, I like knives, so no. Okay, this is how the encrypted disk key is stored in the partition footer or in a file. The key length is 16 bytes. This is the encrypted disk key. This is the IV used by the key derivation function, and I call this section padding. It will be important when discussing the Samsung way. In case of Samsung, the basic idea is the same. A password-based key is used to encrypt the actual encryption key, and the result is stored in the partition footer or in a file. The difference starts here. There are 2 hex constants. They are AES encrypted with the key derived from the password. There are 2 XOR operations. The first operands are the result of the AES encryption. The second operand is the first half and the second half of the encrypted disk key. The clear test key is the concatenation of the XOR results. Samsung also uses the encrypt with AES CBC, and the key derivation uses 4000 cycles with SAJ 256. Remember the Desert Eagle. So it's also easy to remember because it looks like a Star Trek ship.
Captain Kirk.
Yeah. Anyway, the FIPS documentation helped, but I had to debug a lot on ARM stuff to have an idea about the details. The key storage didn't change too much. We have longer key lengths, and the main difference here is the padding. It is not all 0. Let's go through the important differences. In the key derivation function, Samsung uses SAJ256, Android uses SAJ1. And the cycles are different, but not too much. The key length that encrypts the actual encryption key is doubled in case of Samsung. And the padding is used for something. In case of Samsung, it is an age MAC of the encrypted disk key, the encrypted one, not the decrypted one, and the key derivation result. It means that in order to verify a password, you don't have to decrypt the actual key. There is a password verification function in the Volday process. On Android, the Volday process is responsible for handling disk, like mounting operation and disk encryption. When it started, it opens a socket, and you can send commands through this socket. The VDC command can be used to send command to the Volday process. This is how can you send the command. The VDC, anyway, is part of the standard-based Android operating system. You need root privileges or system user privileges. In the first example, we sent an incorrect password. In the second example, we send the correct one. As you can see, or rather you cannot, there is no difference in the terminal output. However, if we check the system logs with the logcat utility, we see in the first attempt the password was incorrect. This is how it works on S4, but it doesn't work on S2 and S3. And when I'm speaking about S2 and S3, I mean their own variants too. So, okay, as a result, we have an on-device password cracking engine. Well, it's terribly slow. That's why I made the decision to dig deeper into the Samsung implementation. On Android, the relevant function is called from the cryptfs.c of Volday. In case of S4, the verify_edk is called from the libsec_kem.so library. Let's see how things work together on the stock Android. This is an excerpt from the cryptfs.c. The decrypt master key is called to decrypt the encrypted key called master key here with the supplied password. The result is stored in the decrypted master key array. Then, the decrypted master key array is compared to the saved master key. And there is a sleep call against brute force attacks. Nice try, isn't it? But wait, we have a saved master key here. Strange may it seem, but in the Volday process memory, you can find the clear test encryption key. Fortunately enough, it runs as root, so you need root privileges to dump it. And Samsung S4, the verify_edk is called. It generates a padding with the help of the key derivation function and the age MAC of the encrypted disk key and the key derivation result. Then it compares the generated padding with the stored padding. Cool. It seems apparently Samsung doesn't need to decrypt the actual key to verify a password. Unfortunately, this is not true in case of S2 and S3. I didn't find the clear test key in the Volday memory on an S4 form. And we have a live demo for this one.
Yes, but before the first live demo, we have a surprise for you guys because we want to give you something special, and the most special thing in a hacker conference is a girl. Okay, now we have at least 4 girls in the room, so thank you. But anyway, we have a really special guest for you. Her name is Sandy. She's beautiful. So guys, please welcome Sandy. Yeah, she's hot. So, she's beautiful. She loves hacking. She doesn't talk too much. So, let's say she's the perfect girlfriend.
Take it easy. I have a wife and he has a girlfriend.
Yeah. But we spent a lot of nights with Sandy. So, yeah, we have upset girlfriends at home. Okay, so seriously, Sandy is a framework written in Python. And when Laszlo started to came up with his results, there were two ways. First, to develop single scripts and programs for all of his results, or put everything together and create a kind of framework. So this is how Sandy was born. And yes, we made the first mistake of all programmers. We designed and implemented Sandy from scratch. So she is unique, let's say.
And cute.
And cute, yeah, sure. OK, so let's start with the demo. First, we're going to use S3 device. It's booted. It's encrypted, of course, and it's logged with a password. So as you can see, Sandy has two main options. You can deal with phone stuff, or you can deal with SD card stuff. So let's go for the phone one. And now we will play with the VoLD process, as Laszlo just mentioned. So in case of every module of Sandy, there are some parameters you should set up. But in most of the cases, you can leave the defaults on, and it's going to work in most of the cases. So let's see what happened. As you can see, Sandy loves colors. She's a girl, you know. We just found the VoLD process. This is the process ID. And then we spot the relevant memory segment from the prots file system. We uploaded a tiny binary. It's a memory dumper. It's precompiled and bundled with Sandy, so you have nothing to do with this, just use it. And of course, we downloaded the dump file from the phone, and we clean up the phone. Oops, sorry. And this is the interesting part. Actually, this is a strings output of the given memory dump file. And if you take a look at the last line, just let's zoom it. It is the clear text password of this phone. So you can unlock this phone with this password. It's in the memory dump in clear text. And there are some other green stuff here. These are the candidates for the device encryption key, because it's not so easy to find. Based on the location of the clear text password, you can find device encryption key candidates. But based on our testing, in most of the cases, you can use the first one, and it works. We save the results to these key files. But what's the point? So what can you do with this key file thing? Let's say you have a DD image from an encrypted phone. You can mount that encrypted DD image with the help of these key files. So let's try it. I say, OK, I want to mount. I want to mount, and I want to use a key file because I have one. And yeah, fortunately enough, we have a DD image from this S3 phone. And we're going to use this key file, and the result will be in the user data folder. So just let's run it. And we just use this normal script setup tool, so it's not magic. But now if you take a look at the user data folder, here is the content of an encrypted DD image from an S3 device in clear text. So, yeah. Thanks. And it worked. Yes. OK, so let's go back to the show.
Sorry. Besides the clear text encryption key, you can find the actual password too in the VoLD process memory. This works on an S2 and S3 versions. Of course, you need root privileges, and we used Android debug bridge on our module. And I know, if you have root privileges, the game is over. I'm sure several methods can be developed to get the same information. However, now you have one, and it can come handy in certain circumstances. But what if we do not have this level of access? We can still try the offline brute force attack. To mount such an attack, we need to create a recovery image. You need ADB, root, and the DD command in it. And use the DD command through ADB to dump the partition footer, the last 16 kilobytes of the encrypted partition, and try to crack it. And we will show you how.
So, demo again. I hope so. So this time we go for this dump footer option. So we're going to dump the last 16K of the partition in order to carry out such kind of offline password cracking attack. So default values are fine again. And yeah, so there is a warning. In a forensic situation, you shouldn't use this module because, as you can see, we just upload a custom binary to the phone. It's called seek and read in order to get the last 16K of the partition. Of course, you can use DD because there is DD, but it's terribly slow. So we are talking about a 9 or 10 gigs partition, so it takes minutes to get the last 16K because DD just reads through the whole partition to seek. So this is why we have this seek and read binary. Again, it's bundled with Sandy. So yeah.
If you need something forensically sound or something like that, Sandy has a module that can dump the footer from a DD image.
Yeah.
So if you need Sandy in that cases, you can use that module.
Yeah. Surprisingly, the name is dump footer from DD, so it's really hard to find. Okay, so we've got the footer file. What's next? As Laszlo mentioned, we are going for a kind of offline cracking, so it would be great to crack the password somehow from the footer. And we have a module called convert to GTR. And it may look familiar with you. It's some kind of format that John the Ripper likes. So let's use John in order to crack this password. There is one small problem. There is no support for Samsung encryption in John, not even in the Jumbo version. You may find support for Android, the stock Android encryption on GitHub. It's not in the release, but it's on GitHub. But there is nothing for Samsung encryption. So Laszlo developed a new module or format plugin for the Jumbo version. It's called SendCrypt. So now you can use John in order to crack Samsung encrypted password. And as you can see, we use a dictionary file because we have a so complex and so secret password. So yeah, we need a dictionary file because it would take ages to crack it without the dictionary file. So, and yes, as you can see, we just cracked the password with John. As I said, it's really complex. It's really hard to crack. By the way, it's our favorite password. So yeah. So now you have the password from the footer. And we just cracked it with John, so it's kind of cool.
Okay. If you have the algorithm, it's fairly easy to develop a brute forcer. I chose the John the Ripper platform. This was my first John the Ripper module. And by the way, I was astonished how easy to develop or add the module to the Jumbo version. The module is far from being optimized. For example, I didn't implement the OpenMP support yet. 1.8 version of John supports the parallel running for all modules. Unfortunately, it hasn't been ported to the Jumbo version yet. It's kind of slow because of the 4,000 cycles in the key derivation function, like in the case of the WPA pressure key authentication of the wireless world. Samsung has a password policy when you set up the encryption. Unfortunately, it's not an extremely strong one. So the dictionary attack on a CPU is feasible against the weak password. Of course, higher speed can be achieved on a GPU. We assume, because we did not test it, a brute force attack and a GPU implementation is feasible against the weak password. The moral of the story is that the weakest link is always the user, even weaker when it comes to a mobile device. Just try to type in a strong password into a mobile device, like dancing tango with tight feet. And this method doesn't work on S4, because with S4, Samsung went further. The key storage changed. We have the same key lengths, but we have an encrypted footer here. ARM introduced TrustZone into CPUs, a trusted execution environment. As a rough definition, it is a hardware-based separation of an execution environment. It is separated and protected from the normal mode calls. On Samsung phones, there is a kernel called MobiCore which was developed by a German company called G&D. You can have trustlets above this kernel for a specific purpose. An S4, one of them is used for the phone encryption. However, VoLDE is still there, as you saw, and the VDC can be used. The VoLDE sends the data from the partition footer to the secure storage daemon. And the secure storage daemon communicates with the Mobicore environment, with kernel drivers, and with the help of the client library. Maybe that's just me, but this one reminds me for a glass of beer. So easy to remember. VoLDE calls this function, of course, at the end of a chain from a relevant library. And as you can see, it sets up an Android shared memory and sends the file descriptor of the shared memory to the secure storage daemon, and later communicates with the secure storage daemon through this shared memory. The secure storage daemon calls these functions to communicate with the Mobicore environment. There is a very good analysis and the SensePost blog. How can you analyze this method of communication? The MC open session is called to set up a session to the given trustlet. And the supply UID can be used to identify the trustlet on the disk. In theory, it should be signed or encrypted according to the SensePost blocks. But when I check the strings in it, I get back this snippet. As you can see, at least some part of it is not encrypted. At this stage, I was very happy. This could be an awesome research. Unfortunately, everything can be solved in a much easier way. It will be a nice research in the future for somebody or for me. But now I need just an offline brute forcer, and it can be solved pretty easily. Just create a recovery image with the running Mobicore environment. Attach a debugger to the VoLDE process and set a breakpoint on the verify_edk function. Run VDC to initiate the password verification, and then all you need is to dump the first parameter of the verify_edk function. And we have a live demo for this one.
Yes, the most interesting live demo, because there are a lot of things that I shouldn't forget. So just give me a few seconds because I have to clean up a bit. And I just restart Sandy. I will tell you why. Now I just restart her, or it, or whatever. Okay, so let's change the phones, because we have an S4. Whoa, so we have an S4, the brand new flagship of Samsung. It's booted into this special recovery mode, but it's not a big deal because most of the Samsung phones can be booted in any recovery, so it's not a big deal at all. So just let's connect it. Oh yeah, it will work. Okay, so again, we're dealing with phone, and we go for this S4 module of Sandy. Default values are fine. A lot of text. So what happened? We just uploaded GDB server to the phone. Again, it's precompiled and bundled with Sandy, so you can use it. We started the GDB server on this port, and we just attach a remote GDB to the server. So it's a kind of remote debugging, standard stuff. There are two precompiled versions of GDB in Sandy. You have one for Macintosh and you have one for Kali Linux, so we can use them. And then we just find the VoLDE process, attach the given thread of the VoLDE process, set a breakpoint to the verify_edk function, as Laszlo mentioned, and we just initiate a VDC call with any password just to hit that breakpoint. And when the breakpoint is hit, all you need is to dump the first parameter. The trick is this is ARM, so you need the R0 register, which points to the first parameter, and that's all. Then we have the footer file again, and we have the John-compatible format of the password in order to crack it. So basically, you can use the same John module in order to crack the password from an S4 device. So let's try it. And yes, we just cracked the password of an S4 device. Again, as I said, we love this password. We use it all the time, so yeah.
Even on Gmail. So please don't try it.
No, they can't. That's a capital Q.
Yeah, sorry, it's capital Q.
No, so, okay. Whatever. So, okay. So we get the key again. And there is one more thing. So we've got the password. First, we can unlock the device for sure. But we can do the same mounting stuff if you have an encrypted DD image from an S4 device, as we just saw in the case of S3. So just let's try it. I want to mount, and I want to mount from password. So I have a DD image from an encrypted S4 device. And yes, fortunately, the default value of the password parameter is our secret password. So this is the case when you should change the value of the default parameter, because I don't think you use the same password. Or please, use the same password.
It's under GPL, you can use it.
Yeah, no problem. We use the same crypt setup stuff, so, and we check the user data folder, the content of an encrypted DD image from an S4 device, again, or no, just like in case of S3, whatever. So, go back to the presentation.
So Thanks. What you saw is that in the first parameter, there is the encrypted disk key of the verify_edk function. And it is in the same format as for S2 and S3. And it is encrypted in the same way. So you can use the same John Doe repair code to crack it. So despite the TrustZone and MobiCore magic, we still have an offline brute force capability. Cool, isn't it? And to step further, it's quite easy to create a recovery image in case of Samsung. You can find in the Sandy recovery folder the ini.rc and default.rots file. Just overwrite the originals with them. And you can find the TXT file there that helps you to create your recovery image. The trick is to use the original Samsung firmware to have a genuine Samsung kernel, so to loading the MobiCore kernel drivers is easy. And we did not finish here, because Samsung supports SD card encryption. As a downside, the most annoying thing is that you cannot use your encrypted SD card in a different phone or in a PC. So it's worth investigating deeper. It uses the well-known encryptFS file encryption engine. It encrypts every file separately. The encrypted encryption key is stored in the following file, and in the same format as for the S2 and S3 disk encryption, and the same encryption is used, so you can use the same John Doe repair model to crack it. Boring. But what's wrong with this picture? For a beer, anyone?
2 beers? Come on, it's easy.
Readable by everybody.
Yeah?
Come to us for the beer.
Yeah.
I'm 19.
Yo! And this is US. You know, in Hungary you could drink it.
So, glass of water?
Okay, so the file is word readable on S2403. It is well protected on S3 and S4. The root user can access it only. However, the first S3s came with 403. The file is word readable on those phones. And if you encrypted your SD card before the upgrade, the file is still word readable. My boss's phone behaved exactly the same way. It received the upgrade from Samsung. It's on 412, but the file is still word readable. On the right side, you can see a screenshot from a zero privilege app that shows the encrypted disk key from the file. And the first 8 bytes needs more explanation. encryptFS uses key rings, and you can manipulate the key rings with the keyctl command on Linux. I compiled the keyctl for ARM and ran it on the phone as root. With the show subcommands, you can print out the key list for a specified key ring. With the key identifier from the output, you can print the clear text encryption key with the print sum command. This is how can you back up your encrypted SD card clear text key. So one problem solved. Then we ran the mount command with normal user privileges. The encryptfs underscore sig shows which key was used for mount. On Samsung phones, this is the first 8 bytes of the clear text key. So you can have the first 8 bytes of the clear text key with a 0 privileged app. It reduces the key length from 256 to 192. In reality, it's not a big thing. However, it's strange because everybody can run the mount command. And we have live demo for the SD card stuff too.
Yes, all I need is to, no, first just restart Sandy again. She's a girl, you know, so. So just restart Sandy. Yep, and change the phones. Back to the old S3.
This would work on an S4, just we wouldn't like waste your time with rebooting the S4. Because I think it's better to waste the time with Sandy.
Yeah, it's always better. Okay, so this time let's go for the SD card option. First, I just show you the get key file function. It just downloads the key file, as Laszlo mentioned. It's not a big deal. It's just an ADB pool from the phone. So yeah, you just download the key file. And of course, you can convert it to John format. So you can use the very same John module in order to crack it. So it's boring. I won't show you because you saw the module 2 times. So let's move on. Let's move on to the key CTL stuff because it's much more interesting. Default values are fine. And so we just upload the key CTL utility. Again, it's bundled with Sandy, so nothing to do with it. And we just run the key CTL show command. And here is the key ID, what we need. And with this key ID, we can dump the clear text SD card encryption key. And we just download it from the phone and clean up the phone for sure. So we've got the clear text SD card encryption key. What's next? Let's say we have a file. We have a file from an encrypted SD card. Here is a file. Let's try to check the content. It's garbage. Of course, it's encrypted. So let's try to somehow mount this file with Sandy. And yes, a key file. So we're going to use this key file. We're going to mount the files from this folder, and the result will be in the SD card folder. So let's try it. We just add the given key to the keyring because we use keyrings, and then we just use the normal mount command with the given parameter to mount it. And this is the first 8 byte of the clear text key, as Laszlo mentioned. So if it worked, and we check the SD card folder, here is the same file, but now we have, it's really sensitive and really secure content. Sensitive mail attachment, okay.
It's not so important, it's not a home movie.
Yeah. Yeah, sorry, it's not a whole movie, but we have a different demo for that, so. Okay.
One more thing. We know, last year we had a mobile part in our database presentation. This year we have a database part in our mobile presentation. We know it's far-fetched, but it's about crypto and it will be fun, you will see. We talk about how Oracle stores the database password links. With the help of a database link, you can access a remote database while you are logged into a database. You can create a database link in a way when the username and password of the remote database is stored in a normal table, the linked dollar table. And then when the user tries access the database link, he doesn't have to know the username and password of the remote database. This is the old way, how the password was stored. When you see 05, in Oracle at the beginning of a hex strings, you can be sure it is des-encrypted. And the first 8 bytes is the encryption key. And the screenshot, you can see how to decrypt it. Just choose the first 8 bytes as a key, except the 05. The rest will be the encrypted password, and call des to decrypt it. So as simple as that. Sorry, I know it, just give it time. Next, as you can see, from version 11.12.03, the key storage, well, the password storage changed. We have a longer hex string here, in the same table and in the same column. This is how can you call our Python script to decrypt it. Just provide the version number and the very long hex string to it. The first run failed, because by default, SQL Plus prints out the first 255 characters. The SQL Plus is the default connecting command line sync to the Oracle. Fortunately enough, the algorithm itself is so robust, you can put any hex string at the end, and it will decrypt it. The algorithm is so robust, the Python crypt itself is 83 kilobytes long. Okay, I'm joking, so it's not so complex. It's not long because of the complexity. The algorithm itself is fairly simple. It takes only 1 page, but there is a 16K long constants in it. And this constants is used to pick bytes from the long hex string. The pick bytes XORed to another constant. It's not really a constant, but now it is a constant. The result will be an AES key and the encrypted password. And you can just call AES to decrypt it. So as simple as that. The Oracle changed the constant from version 11 to version 12. Our Python script supports both versions. The linked dollar table is well protected. The sysdba can access only. The Oracle needs this password as clear text. So it's not a security vulnerability. However, and I should call this an obfuscation, not an encryption. But however, this knowledge can handy in a post-exploitation phase. So we are pen testers, isn't it? Or aren't it? Okay, as a summary, we showed you how can you dump the clear text key and the password from a Samsung phone memory. We showed the TrustZone is just another security technology, hopefully not an AV, and just should be used in the right way. We solved the mystery of the SD card encryption and the Samsung phones. And we demonstrated playing and hacking Oracle is always fun. So thank you very much for your attention. These are our references, sorry. And you can download everything from GitHub now, and the presentation from our webpage. And please don't try to find me on Facebook.
By the way, we have time, so I'm going to give you a brief introduction of using Sandy as a client or end user or whatever. So there are some things you should know about Sandy. Just quit. So first of all, when you start Sandy, you must supply a project name. It's mandatory because everything is based on projects. For example, if you take a look at the results folder, there is a folder called results. Every module that creates a file or just dumps something, create a file in the results folder. And as you can see, there is a naming convention. Let's say project name, underscore, and the given file name. This is how the different modules try to exchange data. Of course, you can use any file names and you can just reconfigure the module parameters, but to be on the safe side.
And please use simple project name.
Yeah. So to be on the safe side, just use the default naming convention because that's how it works. So this is why I restarted Sandy all the time, because when I change the phone, I just change the project from S4 to S3 and vice versa. So that's the way how it works. By the way, if you have DD images, you should put them into the results folder as well. If you have unencrypted files from SD card, you should put into this folder as well. So this is why you need to supply a project name to Sandy. There is one more thing. There is a config file in the root folder of Sandy. So basically, as we said, it's really important to identify the given Android version on the given phone. So everything based really depends on the phone type of phone version and the Android version. So this is why we need this configuration file, because on some phones there may be the data partition on a different, let's say, block device.
For the Android, just the data partition is encrypted.
Yeah, maybe there is
As you can see, it varies from version to version.
Yeah, maybe there is a different file for the SD card encryption key or a different offset for the footer. So it's kind of cool. So if you have a Samsung device and you want to play with Sandy, please do it. Test it with Sandy, and if you can just extend this configuration file, please do it and contribute it back to the community, because we just tested with our phones. For example, this S3 is my previous private phone, and we
both the S4 together.
Yeah. So if you have Android phones, please play with Sandy. It's fun. If you have any comments or if you find a bug, please send us, and we will do our best to fix Sandy, make her better, whatever. So, yeah, and by the way, if you have any questions, please feel free. By the way, we don't speak English, but we do our best. So, thank you guys.